Imagine a world where raindrops are not formed by water, but by atoms. Picture a scenario where each droplet is a cluster of atoms, behaving in ways that defy our everyday understanding of physics. These aren't just any atoms, but ones that have been meticulously cooled and manipulated to reveal the hidden wonders of the quantum realm. These atoms are chilled to temperatures colder than the deepest reaches of outer space. We're talking about temperatures just a fraction of a degree above absolute zero, where the usual rules of physics start to blur, and quantum effects become dominant. This extreme cold is achieved using advanced techniques like laser cooling and magnetic trapping, creating an environment where atoms can be observed in their most fundamental states. This is not science fiction, but the reality of a groundbreaking experiment conducted in 2025. In state-of-the-art laboratories equipped with cutting-edge technology, scientists are pushing the boundaries of what we know about the quantum world. These experiments are meticulously designed and executed, requiring precision and expertise that only the most skilled researchers can provide. Researchers in Italy and Spain have observed something truly remarkable. Through their collaborative efforts, they have managed to create conditions that allow them to witness phenomena that were once purely theoretical. Their work is a testament to the power of international cooperation in the pursuit of scientific knowledge. They created droplets from a unique mixture of atoms. These droplets are not like the ones we see in our everyday lives. They are quantum droplets formed under conditions that allow atoms to interact in ways that are governed by the strange and fascinating rules of quantum mechanics. These droplets, much like raindrops in our atmosphere, shattered into smaller droplets. This shattering process is a complex interplay of forces at the quantum level, providing insights into how matter behaves under extreme conditions. Each droplet's breakup is a dance of atomic interactions, revealing the underlying principles that govern the quantum world. This remarkable phenomenon provides a glimpse into the quantum world. It shows us how particles can behave in ways that are completely counterintuitive, challenging our classical understanding of physics. The interactions observed in these experiments are a window into the fundamental nature of reality, where particles can exist in multiple states simultaneously and influence each other instantaneously over vast distances. It also hints at the exciting possibilities that lie ahead. The knowledge gained from these experiments could pave the way for new technologies that harness the power of quantum mechanics. Imagine computers that can solve problems in seconds that would take today's supercomputers millennia, or communication systems that are completely secure from eavesdropping. This discovery, published in the prestigious journal Nature, has sent ripples of excitement throughout the scientific community. The publication of these findings is a significant milestone, highlighting the importance and impact of this research. It has sparked discussions and further investigations, as scientists around the world seek to build on this groundbreaking work. It opens up new avenues for understanding the behavior of matter at its most fundamental level. By studying these quantum droplets, researchers can gain deeper insights into the forces and interactions that govern the universe. This knowledge could lead to new theories and models that better explain the complexities of the quantum world. The experiment also offers tantalizing clues for developing future quantum technologies. The principles observed in these droplets could be applied to create more efficient quantum computers, advanced sensors, and other technologies that leverage the unique properties of quantum mechanics. The future of technology is quantum, and these experiments are a crucial step towards realizing that future. The experiment involved cooling a mixture of two different types of atoms, potassium-41 and rubidium-87. These atoms were trapped and cooled down to temperatures just a few billionths of a degree above absolute zero. This is far colder than the vast emptiness of interstellar space. To achieve these ultra-cold temperatures, the researchers used a combination of laser cooling and evaporative cooling techniques. They then trapped the atoms within an optical waveguide. This waveguide acted as a microscopic channel, confining the atoms to a one-dimensional space. Within this optical waveguide, something incredible happened. The ultra-cold atoms started to clump together, forming tiny self-bound droplets. These droplets, held together by a delicate balance of forces, exhibited a behavior never before observed in the quantum world. The formation and subsequent shattering of these quantum droplets can be understood by considering two opposing forces at play. These forces, though seemingly simple, are deeply rooted in the fundamental principles of physics and chemistry. They govern not just the behavior of quantum droplets, but also have implications in various other phenomena observed in nature and technology. The first is surface tension, a force that tends to minimize the surface area of a liquid. Surface tension is a result of the cohesive forces between liquid molecules. It is the reason why water forms droplets and why insects can walk on water. This force acts like an invisible skin, pulling the molecules at the surface together and making the liquid behave as if it were covered with a stretched elastic membrane. Just like water droplets forming beads on a window pane, surface tension tries to pull the quantum droplet into a spherical shape. This spherical shape is the most efficient way to minimize surface area for a given volume, which is why we often see droplets taking on this form. The same principle applies to quantum droplets, where surface tension works tirelessly to maintain this minimal surface area configuration. The second force is quantum pressure, a consequence of Heisenberg's uncertainty principle. This principle is a cornerstone of quantum mechanics, stating that there is a fundamental limit to how precisely we can know both the position and momentum of a particle. This uncertainty is not due to any flaws in measurement, but is an intrinsic property of the quantum world. This principle states that you cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely you know one, the less precisely you can know the other. This inherent uncertainty gives rise to quantum pressure, a force that acts against the confinement of particles. In the context of quantum droplets, this pressure works against the surface tension, trying to pull the droplet into a tight, spherical shape. In the ultra-cold realm of these quantum droplets, this uncertainty in momentum translates into a pressure that counteracts the inward pull of surface tension. At temperatures close to absolute zero, particles exhibit behaviors that are starkly different from those at higher temperatures. The quantum pressure becomes significant enough to influence the stability of the droplet, creating a delicate balance between the two forces. The interplay between these two forces determines the stability of the quantum droplet. If the surface tension is strong enough to overcome the quantum pressure, the droplet remains stable and maintains its shape. However, if the quantum pressure is too strong, it can disrupt this balance, leading to the droplet's instability and eventual shattering. If surface tension dominates, the droplet remains stable. This stability is crucial for various applications, including in the fields of material science and nanotechnology, where controlling the shape and stability of droplets can lead to advancements in creating new materials and devices. However, if quantum pressure gains the upper hand, the droplet becomes unstable and can shatter. This shattering can be both a challenge and an opportunity. Understanding the conditions under which droplets become unstable can help scientists develop better control mechanisms for quantum systems, potentially leading to breakthroughs in quantum computing and other cutting-edge technologies. The shattering of these quantum droplets is a beautiful manifestation of a phenomenon known as the Plateau-Rayleigh instability. This instability is a fascinating process that occurs when a stream of liquid, such as water, breaks up into smaller droplets. It's a phenomenon that can be observed in everyday life, like when you see water dripping from a faucet or when a stream of water breaks into droplets as it falls. This instability, first observed in classical fluids like water jets, describes how a cylindrical column of liquid breaks up into smaller droplets due to surface tension. Surface tension is the force that causes the surface of a liquid to behave like a stretched elastic sheet. It's the same force that allows insects to walk on water and causes water droplets to form beads on a surface. However, in the quantum world, things get even more interesting. Quantum mechanics, the branch of physics that deals with the behavior of particles on a very small scale, introduces new and intriguing phenomena that do not have counterparts in the classical world. One of these phenomena is the presence of quantum fluctuations. The presence of quantum fluctuations, tiny variations in energy that are inherent to quantum systems, modifies the strength of the interactions between the atoms. These fluctuations are a fundamental aspect of quantum mechanics and arise from the uncertainty principle, which states that it is impossible to know both the position and momentum of a particle with absolute certainty. This modification, known as the Lee-Huang-Yang correction, plays a crucial role in determining the fate of the quantum droplets. The Lee-Huang-Yang correction is a theoretical adjustment that accounts for the effects of quantum fluctuations on the interactions between particles. It was first proposed by physicists T.D. Lee, Kersen Huang, and C.N. Yang in the 1950s. The Lee-Huang-Yang correction effectively weakens the attractive forces between the atoms, making the droplets more susceptible to the Plateau-Rayleigh instability. This weakening of the forces means that the quantum droplets are less stable and more likely to break apart into smaller droplets. This is why the quantum droplets, unlike their classical counterparts, shatter even at relatively small sizes. In the classical world, droplets need to reach a certain size before they become unstable and break apart. However, in the quantum world, the presence of quantum fluctuations and the Lee-Huang-Yang correction mean that even very small droplets can become unstable and shatter. This fascinating interplay between quantum mechanics and fluid dynamics opens up new avenues for research and has potential applications in fields ranging from material science to quantum computing.